This lecture continues the presentation of the direct stiffness method. The material introduced facilitates the application of the method in realistic problems of structural analysis. The frame finite element is examined, which can be used to analyze most skeletal structures. It can also be used to form derivative finite elements, such as the truss, the shaft, and the beam. The transformation of the coordinate system from local to global is explained, which is essential in analyzing structures in the three-dimensional space. In a wide range of applications, the loads are applied between the nodes of the structure, the treatment of which is presented in the last section. The lecture closes with application examples. In this section, the work due to the element deformation is examined. Expressions for the internal and external work on the structural member are derived, through which the principle of conservation of energy is proved. Vectors are introduced for the representation of the forces and displacements, which have magnitude and direction. Finally, it is explained that the work due to deformation can be calculated through the dot vector product. The top figure shows a structural member that is fixed at the left support and free to deform longitudinally at the right support. A constant force F1 is applied to the right end, the direction of which is parallel to the longitudinal axis of the member. And displacement delta 1 is observed. The differential external work dW is equal to the force function F delta times the differential displacement d delta. The external work W is equal to the integral of the force function F delta integrated with respect to d delta between 0 and delta 1. In this case, the force is a nonlinear function of the displacement. This is shown graphically in the bottom figure. The internal work, U, is equal to the volume of the element, which is given by the product of the length times area, times the integral of the stress, integrated with respect to the differential strain, d epsilon. This relationship can be further manipulated to become equal to the integral of the force function, F delta, integrated with respect to the differential displacement, d delta, between 0 and delta 1. Finally, due to the principle of conservation of energy, we can observe that the external work is equal to the internal work. We now examine the case that the forcing function F delta is linear. In this case, F delta is equal to K delta, where K is the stiffness. The external work, W, is equal to the integral of the forcing function, F delta, integrated with respect to d delta, between 0 and delta 1. This equation can be further manipulated to become equal to K times delta 1 squared divided by 2. Since F1 is equal to K times delta 1, the external work can be expressed as W equals F1 times delta 1 divided by 2. This is shown graphically in the bottom figure. The internal work, U, is equal to the volume of the element, which is given by the product of the length times the area times the integral of the stress integrated with respect to the differential strain d epsilon between 0 and epsilon 1. This relationship can be further manipulated to become equal to F1 times delta 1 divided by 2. We can observe that the principle of conservation of energy applies, since the expression for the external work is equal to the expression for the internal work. We now examine the case that the force is applied at an angle phi to the longitudinal axis, as shown in the figure. The force component in the direction of the displacement is equal to F cos phi. The equation for the external work due to displacement delta 1 becomes W equals the integral of the forcing function F delta times cos phi integrated with respect to d delta between 0 and delta 1. A more scientific representation for the applied force and displacement can now be introduced. Both have magnitude and direction. Therefore, they can both be represented using vectors. In the present context, F represents the force vector and delta the displacement vector. The middle diagram shows a vector representation of the deformation of the member shown in the left figure, where the node represents the end point of the structural member. The force vector, together with its components on the two orthogonal axes, are presented in the right diagram. An alternative, mathematically consistent way of representing the work is through the dot vector product. The dot product is also called scalar product because it returns a scalar value. The external work W is equal to 1/2 times the dot product of vectors F and delta. This product can be rewritten as 1/2 times the magnitude of vectors F and delta times the cosine of phi. The dot product for the external work can also be expressed using matrix notation. In this case, W equals 1/2 times the transpose of F times delta. The equation is rewritten by substituting the vectors. In its final form, the work is equal to 1/2 times F times the cosine of phi times delta. This equation can be used to evaluate the work on a structural system when vector F represents the system of nodal forces. The equation for the external work can be transformed into an expression consisting exclusively of the displacement vector and the stiffness matrix, using the equation F equals K times delta, converted to its transpose. The final form of the equation for the external work is W equals 1/2 times the transpose of delta times K times delta.